let's look at a simple example and try. I'm picking one where we could both do it explicitly and implicitly and show that you get the same thing. So if I was going to do it explicitly, it means like you solve for y first. So that's 1 over x. Or I could rewrite it as y is equal to x to the negative 1. And then I would take the derivative with respect to x. So dy dx is equal to negative 1 x to the negative 2, which then become negative 1 over x squared. That's one way. And the other way is to do it using implicit differentiation. And I'm literally just picking so that you can see that ultimately in the end, we will get the same value. So in this particular case, I have to use the product rule. So we end up with the first times the derivative of the second, that's dy dx, plus the second times the derivative of the first, which is just 1. And then on the other side of the equal sign, the derivative is equal to 0. And we end up with dy dx is equal to 1 over, so here, no, negative y over x like that. Are they the same thing? That's the question. Well, yeah, because just keep in mind that when I solve this explicitly, y is actually equal to 1 over x. So I could rewrite this as negative y times 1 over x, which is negative 1 over x, that's y is 1 over x, times 1 over x, which is equal to negative 1 over x squared. So they do end up being the same thing. One has an x and a y in it, and the other doesn't. Most people prefer the explicit version, but you know, everybody has their own preference. And if you have an order pair and it's easier for you to do it implicitly, go right ahead. Now, there are questions that you can't do implicitly. So, or explicitly, I mean. So it becomes a lot harder to solve for y, for example, in example 4. So we don't really have an option there. So in this case, we're going to have to do d dx of x plus xy plus y is equal to d dx of y squared, indicating that we're taking the derivative of both sides. That's going to give me a 1 plus. Now I have to use the product rule. That's where most people mess up on this. X times the derivative of the second, dy dx, plus the second times the derivative of the first is just 1, plus the derivative. So just to highlight, this here is where I use the product rule, and I highlight it in yellow. And then the derivative of y is dy dx is equal to, and then 2y, and again using the train rule, dy dx. And then I'm going to solve for dy dx by moving all of the terms with dy dx to one side. I think it's just easier to leave it as 1 plus y is equal to 2y dy dx minus x dy dx minus dy dx. So then I end up with dy dx is equal to 1 plus y in the numerator. And look, if I factor out a dy dx in the denominator, I get 2y minus x minus 1. So then it says find all the points on the graph where the tangent is horizontal. Well, just like the problem before, tangent is horizontal when dy dx is equal to 0. So dy dx is equal to 0 in this case when y is equal to, not y, that's the numerator, when 1 plus y is equal to 0. So that means when y is equal to negative 1. So it says find all the points where that happens. Okay, so we got to do a little bit of work to find that. Let's see if we can do it without a calculator first. So when y is equal to -1, I have to substitute back into the original function or not function, but relation to find out, whoa, that's not an x, I'm substituting in for y. So that is going to be x times -1 plus -1 equals -1 squared. Okay, so we get x minus x, plus -1 is equal to 1. These cancel out. That's a false statement. If that's the case, since there are no points where y is equal to -1, there are no horizontal tangent lines. That's how you do that. All right, write an equation in x which is satisfied by the point xy on the curve where the tangent is vertical. Then use your calculator to solve for x. All right, let's see what happens. First of all, vertical tangents when dy dx is undefined. So that means so that implies when 2y minus x minus 1 is equal to 0. So in other words, when, and that's actually a line here, so you could say, when 2y is equal to x plus 1, or when y is equal to x plus 1 over 2. That means, okay, I have to substitute in this value into the original to find the points so that I can find the x values where that happens. Now, if there was asking for the y values, then I would solve this equation for x instead. But I know that the tangent lines will intersect the function, or not the function, but the relation. So I'm essentially trying to solve this system here. 2y minus x minus 1 is equal to 0, with where that intersects with x plus x y plus y is equal to y squared. And because I want to have it all in terms of x, that's why I'm choosing to solve for y, and then I'm going to substitute that in for y. So then it's going to be x plus x times x plus 1 over 2 plus x plus 1 over 2 is equal to x plus 1 over 2 squared. And guess what? Your graphing calculator will do that for you. You do not have to simplify. You can even leave it exactly like this.